Good afternoon all. Last day we have done the volume integral. Now its application is the divergence theorem. It's the last section of vector calculus in your syllabus. Theorem states that let D be a closed and bounded region in 3 space with a piecewise smooth boundary S that is oriented outward. Let f of xyz is equal to p of xyzi plus q of xyzj plus r of xyzk be a vector field for which p, q and r are continuous, and how continuous first partial derivatives in a region of 3 space containing D. Then double integral over s f dot n ds is equal to triple integral over d div of dv. So we have here we have a surface integral and a volume integral connection is there. Double integral over s f dot n dvs is equal to triple integral over d div of dv. Now we have a problem verifying divergence theorem. Let D be a region bounded by the hemisphere x square plus y square plus z minus 1 all square is equal to 9, 1 less than or equal to z less than or equal to 4, and the plane z equal to 1. Verify the divergence theorem if xi plus yj plus z minus 1 equal to k. So our region is a hemisphere with center 0, 0 and 0, 0, 1 and radius 3, and we have a plane z equal to 1, that is at center. 1 at the point z equal to 1 we have a plane. Now we can verify the divergence theorem. Let's do the problem now. So our region is a hemisphere of center 0, 0, 1 and radius 3. Here f is given as xi plus yj plus zk. So div of equal to first one dou f1 by dou x, which is same as x, dou x by dou x plus dou y by dou y plus dou z by dou z, which is equal to 1 plus 1 plus 1, which is equal to 3. Therefore triple integral over d div of dv is equal to triple integral over d 3 dv, which is equal to 3 into triple integral over v dv, which is equal to 3 into volume of hemisphere of radius 3. So we know that the volume of hemisphere is 2 by 3 pi r cube. So 3 into 2 by 3 pi into our radius is 3 cube, which is equal to 3 cube is 3 and 3 cancels, 3 cube is 27, 27 into 2 pi is equal to 54 pi. So we we have got one side value. Now we have to show that the surface integral, we have to evaluate the surface integral. Double integral over f dot n ds is equal to we have two surfaces actually. One is the hemisphere and the other is the plane z equal to 1. So we have to add these two surface integrals. So s1 is equal to f dot n ds plus integral over s2 f dot n ds, where s1 is the hemisphere and s2 is the plane z equal to 1. So if s1 is the level surface of g of x, y, z is equal to x square plus y square plus z minus 1 all square, then a unit outward normal is n is equal to del g by norm del g, that n is equal to 2xi plus 2yj plus 2 into z minus 1k divided by square root of 4x square plus 4y square plus 4 into z minus 1 all square, which is equal to xi. We can cancel the term 2 from numerator and denominator. From denominator square root of 4, which is equal to 2. So after cancelling we will get xi plus yj plus z minus 1 into k divided by square root of x square plus y square plus z minus 1 all square, which is equal to xi plus yj plus z minus 1 all square z minus 1k all divided by 3. The given sphere is x square plus y square plus z minus 1 all square is equal to 9. So square root of that is 3, which is equal to x by 3i plus y by 3j plus z minus 3k. Now f dot n is equal to xi plus yj plus z minus 1 into k dot x by 3i plus y by 3j plus z minus 1k, which is equal to x square by 3 plus y square by 3 plus z minus 1 all square by 3, which is equal to 1 by 3 into 9 equal to 3. And so double integral over s1 f dot and ds is equal to double integral over s 3 into 3 by square root of 9 minus x square minus y square dA, which is equal to 3 into 3 is 9. We can change the integral term into polar coordinates. So dA becomes r dr d theta. So it becomes 0 to 2 pi, 9 into 0 to 2 pi, 0 to 3, 9 minus r square all raised to minus half, the denominator term. When came to numerator, it becomes minus half into r dr d theta. Now to evaluate the integral, we can substitute, put u equal to 9 minus r square. So du is equal to minus 2r dr. So r dr is equal to minus du by 2. And the limits, when r equal to 0, u equal to 9 minus r square equal to 9. And when r equal to 9, u equal to 9 minus, when u equal to 3, when r equal to 3, this is some small change, this is 3, u equal to 0, which is equal to 9 into 0 to 2 pi, 9 to 0, u raised to minus half minus du by 2 d theta. 9 and minus 1 by 2 we can take outside, that becomes minus 9 by 2. Integral 0 to 2 pi, integral of u raised to minus half is equal to u raised to minus half plus 1 divided by minus half plus 1, which is equal to plus half. So u raised to half by half within the limits 9 to 0 d theta, which is equal to minus 9 by 2 integral 0 to 2 pi. When we substitute the upper limit, it becomes 0 and minus 2 into 9 raised to half d theta, which is equal to minus 9 by 2 integral 0 to 2 pi minus 2 into integral of 9 raised to half is equal to 3 root of 9 d theta. Integral 0 to 2 pi d theta is theta within the limit 2 pi to 0, so the value is 2 pi. So we can multiply minus 9 by 2 minus 2 into 3 into 2 pi. So it becomes 54 pi. On S2, the surface is equal to 1, n equal to minus k, so that f dot n is equal to minus z plus 1. Since z equal to 1 is the plane, so minus z plus 1 is equal to 0. So f dot n ds equal to 0. Now double integral over s f dot n ds is equal to double integral over s1 f dot n ds plus double integral over s2 f dot n ds, which is equal to 54 pi plus 0, which is equal to 54 pi. Therefore triple integral over d div of dv is equal to double integral over s f dot n ds, that is divergence theorem is verified for the problem. Next example is using divergence theorem. If f equal to xyi plus y square zj plus z cube k, evaluate double integral over s f dot n ds, where s is the unit cube defined by 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, 0 less than or equal to z less than or equal to 1. For the evaluation, we use divergence theorem here. And the theorem is double integral over s f dot n ds equal to triple integral over d div of dv. Here f equal to xyi plus y square zj plus z cube k. So div of equal to dou f by dou x plus dou y2 f2 by dou y plus dou f3 by dou z, which is equal to y plus 2yz plus 3z square. Therefore double integral over s f dot n ds is equal to triple integral over d div of dv, which is equal to triple integral over d y plus 2yz plus 3z square dv. The region of integration is the cube, 0 less than or equal to x less than or equal to 1. So 0 less than or equal to y less than or equal to 1 and 0 less than or equal to z less than or equal to 1. Therefore all the limits is from 0 to 1, 0 to 1, 0 to 1, 0 to 1, y plus 2yz plus 3z square dx dy dz. First integrate with respect to x, we get 0 to 1, 0 to 1, y plus 2yz plus 3z square into integral dx is x within the limit 0 to 1, dy dz, so that value is 1. So integral 0 to 1, 0 to 1, y plus 2yz, 3z square dy dz. Now integrate with respect to y. Integral of 0 to 1, integral of y is y square by 2, integral of 2y is 2 into y square by 2, 2 and 2 cancels, and into z plus 3z square y within the limit 0 to 1 with respect to dz. Now which is equal to, when we give the upper limit 1 and lower limit 0, it becomes integral 0 to 1, 1 by 2 plus z plus 3z square dz. Now integrating with respect to z, we get 1 by 2z plus integral of z is z square by 2 plus integral of 3z square is 3 into z cube by 3 within the limit 0 to 1. Now give the upper limit and lower limit. See, upper limit 1 and lower limit 0. So it becomes half plus 3 by 3. 3 by 3 is 1. So 1 plus half is equal to 2.